Maths with Bob. Today we're looking at following on in the series of volume slices and shells 3, and today we're looking at a particular shape. It's called the torus, like a bit like a donut, I suppose, and we're going to be rotating a circle around the x and y axis. Okay, we'll be doing it the same as before. We'll be looking at the seeds and growing the volume. Well, these are the seeds are actually volume elements, and from the volume elements we can actually grow what's called the total volume. Okay, and again, obviously, if we're slicing, remember the bar is always perpendicular to the axis of rotation, and if we're shelling, the bar is always actually parallel to the axis of rotation. Okay, so let's actually just have a quick look at what we're going to be doing. Okay, here we have the circle. Now I can change the center of the circle anyway, but we're going to be looking at a general circle. I'll just show you. I can change the circle. We can actually move it around a little bit. But basically what I've got the surfaces on, so I'm just showing you what's happening. We're going to be generating, you can see here, okay, these are the two donuts around the x and y axis. Now I can actually change, you can see here, change the position of the circle, but really we're going to be looking at a general circle which has center A, B and radius. Now I'll just increase the radius a little bit. Okay, but basically these are the shapes we're going to be looking at, trying to find the volume of. Okay, so the idea is we put the bar in again. You can see here we're looking at a particular circle, which is going to be x minus a all squared plus y minus b all squared equals r squared. Okay, we know that. Hopefully we know that has a center a, b and a radius r. Okay, and we're going to be rotating it around the x and y axes. Okay, now we will encounter a few tricky integrals on the way. We're going to have to use the ideas of odd and even functions, odd and even, well, as applied to integrals as well. We're going to have to use also some trig substitutions, especially when we do the trig substitution for cos squared. Hopefully we all know that's a half of bracket 1 plus cos 2 theta. That's cos squared theta is equal to a half of 1 plus cos 2 theta. This is the substitution we're going to be using. Okay, now I've actually divided it up into two semicircles, actually, in some cases, the top half and the bottom half. But you can see that's where the f and the g are, the two different functions there. Okay, well, first let's do some slicing around the x. Okay, so if we want to slice around the x-axis, first of all, we put the bar in, and you can see it's perpendicular to the x-axis in this case. You will see the bar is in this case a, b, and has well, a couple of different radiuses. Its height obviously is going to be the difference in the two radiuses, and we'll be using that for shells. But you can see here the radius, or the little radius in this case, is you can see here little radius is b minus the square root of r squared minus x minus a all squared. Okay, that's underneath the square root sign, and the big radius you can see here is b plus the square root of all that thing, as before, r squared minus x minus a all squared. Okay, it's just rearranging the circles equation. Okay, we're going to also use the difference of two squares here. R squared minus, well, big R squared minus little r squared, you can see here, can help us sometimes, because big R plus little r is just 2b in this case, and big R minus little r is actually 2 lots of the square root of r squared minus x minus a all squared. Okay, so that's going to help us a little bit with our integration. Okay, well, how will we go about this? Well, the first thing is we know it's a slice, so we use the slice seed. Delta v equals pi big R squared minus little r squared delta x. You can see here. Now, where are we moving from? Well, we're moving along the x-axis. Let's have a look. You might, if you want to go back and have a look, but it's from x equals a minus r up to x is equal to a plus r, and we've already done the calculation of big R plus little r and big R minus little r, and we're going to use, you can see here, when we put that in, we're going to basically well, use well, I guess it's a property of an even integral about from a minus r to a plus r. Okay, is two lots of the integral from a, which is the middle point, to a plus r. Okay, now this integral itself, well, we don't even have to worry about doing, thank goodness. It's just a simple quarter of a circle, 1/4 pi r squared. Okay, you can see here it's a circle of radius r. It is sitting at 0a as the center, and from a to a plus r, you might like to draw that up, but basically it's just going to be a quarter of a circle if you have a look at that. And we can just sum that straight in and get the volume 2b pi squared r squared cubic units. And obviously we'd expect the same volume if we did this calculation by shells, which we're going to be doing, and the integration is actually a bit more complicated. Have a quick look at what we just did. Okay, here we have our slice around the x-axis. Okay, I'll just show you basically what we did. We're obviously slicing, you can see the bar there, CD is moving, okay, up the x-axis, but basically you can see here it's just a series of washes. This is, okay, we've done these calculations, but you can just basically have a quick look at what we just did. Okay, we will actually put the trace on, and I'll try and show you. Let's actually put the trace on, and I'll try and scribe out this shape. I've got to do this reasonably slowly. Okay, hold on. Let's go it over a few times. Okay, so what we've actually done, just have a quick look here. Okay. Where's the slices? Oops. You can see here, I did this fairly roughly. You can see the slices are not terribly. I can actually smooth this out. I'll just hold on. Okay, yes, we can actually smooth this out a little bit. I'll just try and smooth this out a bit more. Just put a few more slices in. There we go. And a few. Because I was doing it fairly quickly. Okay, put a few more slices in over here too. Okay, alright. Okay, alright. So we can actually have a look at this from different angles. Oops. I see it disappeared. It's interesting. Okay, maybe it's better just to just have a look at it like this. Okay, and as it comes around again, we'll just see if we can spot those. Oops, I'll take it back a bit. Have a quick look at these slices. Okay, there they are. You can see there's lots and lots of slices in this particular shape, and I could actually get them a bit closer together if we needed to, but this is just a demonstration of what we're doing. Okay. Okay, we can see here that volume was 2b pi squared r squared. Okay, it wasn't too bad. We used the quarter of a circle idea fairly easily. Okay, we are going to do some slices around the y-axis now, and well, the radiuses are going to obviously change. You can see here the big radius and little radius. We are slicing around the y-axis now as opposed to the x-axis. We've got a few things there. Big R plus little r is now 2a. And you can see here the width of obviously is delta y. We're actually moving, well, the bar being perpendicular to the y-axis actually moves up and down. The y-axis has width delta y, so as you know we need functions of y in our integrals. And okay, again a similar sort of idea. Use the volume seed, delta v for a slice. Delta v equals pi big R squared minus little r squared. In this case, the width of the bar is y, so it's delta y, or if you like, the width of the bar is actually delta y, a small change in y. And we are now going from y equals b minus r up to b plus r. And you can see here with some calculations, you take the limiting value and you end up with the integral pi from b minus r to b plus r 4a square root of r squared minus y minus b all squared dy. And we're going to double up from b to b plus r and use the quarter of a circle idea again. Now you can see here the volume is just 2a pi squared r squared. Okay, well here we are slicing around the y-axis. I'll just move the slice now. Hold on. Here we go. We're slicing around the y. You can see here the washer shapes, different radiuses. Okay. The bar, EF, moving up the y-axis, making everything functions of y in the integration. Okay. Alright, now let's actually try and put the trace on, and let's try and sculpture out this shape. Here we go. Now, I've got to try and do this reasonably slowly, otherwise we have fairly big slices. Okay. Alright, so let's actually have a look. Now, okay. Ooh, there the slices were. They're not too bad this time, actually. I'll just have a quick look back again. Okay, there they are. You can see here there's quite a few of them, and there are a few little gaps which I could smooth out a bit, but this is just give you a bit of an idea of what's happening. Okay, we can then we're now trying to do the integration. It's a different views. You can actually I'll put it back to home view. Okay, all right. So let's actually go and have a look. Okay, at the integration here, and you can see here, as I said before, it's the same, basically using the quarter circle idea. Okay, we're going to move on to shelling shortly, so let's have a look. Okay, now what is the difference between a slice and a shell? Well, as you know, slicing, the bar is perpendicular, and shelling it's parallel to the axis. You can see here we now have just a radius which is normally going to be x or y. Okay, in this case, if we're shelling around the x-axis, it's going to be y. Okay, and basically because the bar is our distance y from the axis, and you can see here we're going to move that up the y-axis, so everything's going to be functions of y. The bar has a width delta y. Okay, and we're going to have to try and basically try and work out what is the height, or if you like, when we flatten out these shells, remember they're rectangular prisms, and their length is the circumference. Okay, their width is in this case delta y, and the height is actually just the length of the bar. You can see AB, and you can see. Let's try and get one of these pens working. Okay, so you can see here we have to do a bit of a calculation here for the height, and obviously it does eventually get to here. Let's see if I can make this. It's supposed to be able to make this circle bigger if you. There we are. There's a bigger circle, or ellipse actually in this case, but h, you can see here, this is the actual length of the bar. Okay, and again, so obviously we are developing everything from the shell volume C, which is basically delta V equals 2 pi RH, in this case delta Y, and you can see here we've actually worked it out. Helps us a little bit with our integration. Okay, well here we have the right page now, and you can see when we are doing shells, okay, we have the volume C as usual, delta V equals 2 pi RH, in this case delta Y, and we've got R as Y, and H is what we worked out before. Now we have to do a little bit more work, okay, on our integration. Actually, before they were just quarter circles, but now with that Y at the front there, basically, well, it means we need to do what's called a trig substitution. And if you let y minus b equal to r sine theta, okay, dy is equal to r cos theta d theta, you see the bounds. Okay, the y bounds. We'll have to change to theta bounds. You can see here I went through that process. Theta minus pi on 2 on the bottom, and up the top it's pi on 2. Okay, so you can see here now our integral turns into a bit more complex, or much more complex integral, you could say. Okay. Now, okay, what do we have to do here? Well, we can simplify it a little bit, because we know that sine and cos, cos squared is actually even, sine theta is actually odd, so the product of an odd and even function is an odd function. So we can use the properties of an odd function integral, if you like, from minus pi on 2 to pi on 2 being 0. Okay, well, that's going to simplify things nicely for us, and just drop us out that b squared r squared cos squared theta part, which we're going to need to integrate. And okay, this is going to be standard trig substitution here for cos squared. You can see here half 1 plus cos 2 theta. You've got to and actually I've doubled up the integration from 0 to pi on 2 now, instead of minus pi on 2 to pi on 2. You can see here using some properties of even function integrals. Okay, and after doing the substitution, okay, let's actually have a quick look over here. This is you can see we've got the 4 pi b r squared, and we've got to integrate the 1 up to theta, and the cos 2 theta obviously is sine 2 theta on 2, and we need to evaluate this, which you can see here. Okay, it's not too bad, and basically it gives us this 2b pi squared r squared cubic units, as we would have got for slicing around the x-axis. Okay, we've got to go back and have a look at that. Okay, so let's actually have a quick look at this. Okay, here we have the shell around the y-axis. Let's actually just move the shell. Here we are. This is the shell. You can see here. I'm just moving the bar CD. Now notice the bar actually is going to have thickness delta x. Therefore, we need functions of x. Okay. Now let's actually try now. Put the trace on for the surface, and see if I can. I'll just try and make lots and lots of cylinders. Okay. Here we go. Oh. Okay, now it's fairly rough, but maybe sometimes it's probably better to be a little bit rough so you can actually see these cylinders. Okay. You can see those cylinders there. Okay. Forming the shape. If you look at this way, you can see how rough they are. I just try and fill these in a little bit better. Okay, just a little bit here and there. I should make the steps a bit finer so we can actually have a look at these. But basically, you can see here the shape is made up of a lot of cylindrical shells. Now this is the torus. Okay. Okay. Alright, so okay, this is okay, the result of our integration, 2b pi squared r squared. Okay, this is shells around the x-axis. We're now going to go on to shells around the y-axis. Okay, and you can see here, if we're going to do a shell around the y-axis, we're going to need basically the radius now, which is now x. The bar is moving along the x-axis with delta x. Okay, need functions of x. Okay, you can see here also I've actually done a few calculations for the height. You can see here, this is, okay, the height. Okay, we're going to use this in the volume element, obviously, and we know the r is just in this case x, and the height we can see here is this expression here. We need to substitute all this into the integration. Okay. Okay, so let's have a quick look. Alright, well, again, we're going to need to do a substitution, a trig substitution. Okay, we're going to get basically because that x at the front of the square root sign there, and we're going to need to let x equal, well, x minus a. I think the easiest way is x minus a equal r sine theta, dx is r cos theta d theta. We're going to need to change the bounds. They're x bounds at the moment, from a minus r to theta bounds. The bottom one is now minus pi on 2, and the top one is actually pi on 2. And again, we're going to get this reasonably complicated integral here. But again, we've got the properties of the odd and even functions. Okay, well, as before, I'll just show you this part here. Okay, this part is going to, because it's a product of an odd and even function, and the bounds, you can see, the bounds, I'll just try and move this across. Okay, pi on 2 minus pi on 2. Okay, because we can use the properties of integrals, okay, odd and even functions, and the actual integrations of those, we can see that that's actually 0, because it actually ends up being an odd function, and the integration from a to minus a would be 0. Okay, and again, we've got to do the substitution. You can see it drops out at this one here, the cos squared one. Okay, and hopefully we've got a bit of experience with integration. We know that we have to do this substitution. Okay, I'll just try to make it a bit bigger. That's the substitution there for cos squared, and obviously we're going to need to integrate that, and you can see here, eventually getting to a pi squared r squared cubic units. Now obviously, shelling around the y-axis, or slicing around the y-axis, we should get the same volume as we did. Okay, we'll just have a quick look finally at this with GeoGebra 5 in 3D. It's pretty amazing. Well, okay, here is our, let's see if we can have a quick look at the different views. Oops, don't think it like that. I see, depending on, okay, this is shells around the y-axis, and you can see here again, okay, they're shells. You should be able to see the slices if there are slices this way, but we turn it like this way. Might even try and actually try to change the view in 3D so we can actually see these shells a bit better. But you can see them on the end here. Just try to look down the y-axis a bit. Okay, here we are. Okay, well, look, I think that's all for today, and thank you very much for watching. Bye for now.